Okay. First of all, I'd like to thank the organizers for this opportunity. So today I'm going to talk on my ongoing project, and I'm going to talk that some renormalization process or regularization process which was used to define knot energies can be applied to integral geometry. So in this talk I'm going to introduce two kinds of Lacan series which can produce functionals on the space of knots or surfaces or in general some manifolds and so on. So it has a similar flavor with integral geometry, especially convex geometry. So in convex geometry there are so-called intrinsic volumes. They have several other names like generalized curvatures or Killing-Lipschitz curvatures or curvature measures or queer mass integral and so on. But anyway, a typical example is the following Steiner formula. Suppose you have a convex body in R3 and then enlarge it a little bit by epsilon. So let omega sub epsilon be a epsilon outer parallel body. That is the union of points so that the distance from that point to omega is smaller than epsilon. Okay, and consider the volume of that. Then the volume can be expanded in a series like this, and then as a constant term you have the volume of the original domain, and then the area of the boundary times epsilon, and the last term is the volume of a ball with radius epsilon, and meanwhile you have epsilon square, and the coefficient is the total mean curvature. Okay, so this is Steiner's formula. So what? Yeah. I forgot. So in our story, we don't use volume. Volume can be considered as the integral of 1 on omega, but we use diverging integral on the product space, which blows up on the diagonal set. And consequently, we have Lacan series instead of Taylor series. And what we get as coefficients are functionals with in somehow global information. So, for example, area or curvature. This is the integral of curvature, and these functionals are integral of something which can be computed locally. For example, curvature can be computed locally. But in our case, we have similar things, but in addition, we have integral of bilocal thing. Something which can be defined on the configuration, 2-point configuration space of omega. Okay. So let me briefly remark on our renormalization. Suppose we are interested in some diverging integral, and suppose the integrand blows up on subset X. Then we consider epsilon neighborhood of this set and remove this set and restrict the integral on the complement of that, and then expand the result in a Lacan series in epsilon. Okay. Then what we are interested in appears in as the coefficient of this Lacan series. And sometimes you need a log term according to the case, and sometimes it's not of this form, but it's of the form that epsilon to some power times Lacan series, and that this power is not an integer. So the power exponents are not necessarily integers. Sometimes you have some shift. Okay. So what we are interested in appears as a coefficient of some of these terms, and sometimes it's the constant term, and sometimes not. So it depends on the. Okay, so as I told you before, I'm going to show you two kinds of Lohan series, and this is the first one. So suppose you have a some manifold in Euclidean space of whatever dimension, okay? And I want to use this notation. So delta sub epsilon is a set of pairs of points in Rn, so that the distance between them is smaller than epsilon, okay? Then we consider this form. So we want to integrate on the product space, but we remove the diagonal set, but we remove epsilon tubular neighborhood of diagonal set, and we want to integrate dx dy over the distance to some power. Then if S is big enough, then it can be expanded in Lohan series, and our renormalized potential energy of omega can be obtained as the coefficient of the constant term. Okay. So in this talk, we studied a case when S being equal to 2m, and in this case, what we finally get is scale invariant. So this method produces several energies, like not energies, which has been introduced in previous talks, called so-called Morvis energy, and also surface energy by Oakley and Saddam. This is a natural generalization of knot energy. Well, there are several methods to generalize knot energies to surfaces. One is to use angles. This is done by Rob and John. But Oakley and Saddam use this kind of renormalization. So I want to use their formulation in this talk. And this energy is for surfaces without boundaries. And if you have a non-empty boundary, then the situation is a little bit different, because you need a renormalization again near the boundary. So recently I defined energies for bounded planar domains with non-empty boundaries with Gilles Solanes in Barcelona. And this can be generalized to higher dimensions. So this method produces several kinds of energies. Okay. And the first three, so knot energy and surface energy and this energy for bounded planar domains, proved to be invariant under Morvis transformations. And if you put S equal to 2m, then this 2m form is invariant under Morvis transformations. But we use this renormalization process. And in the renormalization process, you use distance epsilon. And because the distance is not preserved in Morvis transformations, the Morvis invariance of what we finally get is not an obvious problem. So we need some proof for that. Okay. So this is for notation, and so we want to expand this in a Lohan series in epsilon, but sometimes it is not easy to expand it. So in such a case, we divide the renormalization process into two steps. So, basically, it's a Fubini theorem. So first, you fix point x, and then y can travel in omega, but outside an epsilon ball with center x. Okay. Then as epsilon goes down to 0, then this blows up. So you need kind of a renormalization here, and then you get something finite valued. Then you want to integrate v in omega, but if omega has a non-empty boundary, then again this integral blows up near the boundary. So you need a renormalization process again. Okay. So that was the first Lohan series. And the second Lohan series can be considered as a kind of analogy with Weyl's tube formula. I'm not going into detail of Weyl's tube formula because the idea is very simple. So suppose you have a submanifold M in Rn, say a knot or surface or body or whatever, and let n sub epsilon of M be an epsilon neighborhood of M. In Weyl's tube formula, again, you consider the volume of this, and you expand it in a Taylor series in epsilon. But in this story, we use renormalized potential energy of this neighborhood or the boundary of it. So this is n-dimensional, and this is n-1 dimensional. And then the Loran series starts with epsilon minus n term, and in this case, epsilon minus n minus 1 term. And Loran coefficients will give you functionals on the space of knots and surfaces and body and so on. And some coefficients coincide with the coefficient that appeared in Steiner's formula, but some not. So we have some new functionals. And so when I applied for this talk, I wanted to study the case when M is a knot in R3. And I have a graduate student, and I asked him to do that. And after that, I found the computation is rather complicated. So in this talk, I only deal with the case when n is equal to 2 and M is a planar knot. So that is a simple closed curve in a plane. Okay. So I want to make a brief review of renormalized potential energies. And the first is so-called Morvis energy for knots. And suppose you have a knot in R3. Then you can define V and E as follows. So V is a kind of voltage. So suppose a knot is charged with electrons, then you have the voltage at point P under the assumption that the Coulomb's repelling force is proportional to the distance, the inverse of the distance cube. Okay. So usually we use the arc length to do renormalization, but if you use the distance in the ambient space, the result is same. So for P, you remove the ball with center P, and suppose the rest of the knot is charged with electrons, then the voltage is given by V. And then you can just integrate V or not, then you have the energy. So once you have the energy, then this can be expanded in this form. So the Loran series we have, and it starts with 1 over epsilon term, and the coefficient is the length of the knot, and then comes the energy of the knot, which is information of the global configuration of the knot. Okay. And in the last part of my talk, I need the energy for two-component link, and this can be defined by this. So if you have a two-component link, the energy is the sum of energies of each component plus energy of interactions. And for interactions, because K1 and K2 are disjoint, you don't need any renormalization process here. Okay. So next, I want to proceed to renormalized potential energies for bounded planar domains. That is obtained in a joint work with Gilles Solanes. And for that purpose, I want to begin with renormalized Riesz potential. So suppose in this sheet, I want to begin with general situation. I don't assume that the dimension is 2. So suppose you have a compact body in Rn, and let x be a point in the interior and alpha be any real number. Then consider this integral. Okay. So this is well defined when alpha is positive, and it is called Rees potential when alpha is between 0 and n. That is the case when this is a singular integral but well defined. And this Rees potential has been studied in the first half of the last century. And when alpha is negative, then this integral blows up. And there are several ways to generalize Rees potential to these cases. One is to use analytic continuation. So you consider this number as complex number, then this is well defined when the real part of it is positive. So, and consider this integral as a function of this complex number, and use analytic continuation, and you get a generalization of that, and that is the first method. And the second method is used in the theory of distribution to use Fourier transform. So if you want to decrease alpha by 2, then you apply Fourier transform once, and you multiply by the norm squared, and then you use Fourier transform again. And then what you get is applying Laplacian once, then you can decrease alpha by 2. But the same can be obtained using renormalization. So I want to explain in the third renormalization method. So this explodes when y approaches x. So again, you remove neighborhood, epsilon neighborhood of x, and you restrict the integral. And then the order of explosion is given by this. So you make the difference and take the limit. Then you get a finite valued potential. So I want to call it a renormalized Rees potential. And then it turns out that this can be given by this formula when alpha is negative. So I don't want to explain the case when alpha is exactly equal to 0. But anyway, this is given by the same integral, but you integrate on the complement of the domain, and you put minus here. Okay. So in what follows, I want to study the case when alpha is equal to minus n. Okay, minus n. So this is minus 2n, because this case fits Morris geometry. And if I put alpha equals minus n, then V is equal to the minus of the volume of the image of the complement of the domain of the inversion in a unit sphere with center x. Okay. So I want to proceed to the joint work with Gilles Solanes. And now we have renormalized Rees potential. But if you want to integrate Rees potential on omega, then if alpha is small enough, then it tends to minus infinity. So how to renormalize it? And in what follows, I only explain in the case when n is equal to 2 and alpha is equal to minus 2. Then if you have a bounded domain in the plane, if a point in the interior approaches the boundary from inside, then this potential tends to minus infinity, but the order of the asymptotic can be expressed by this formula. Okay. So again, you can renormalize the integral of V, and you put you can define the renormalized potential energy by this formula. So this term will give you this term, and you have 1 over delta term here with curvature with coefficient, but this term is killed in the integration of this one. So you don't have a log term here. Okay. Then again, we have Laurent series. So if you remove neighborhood of the diagonal set in the product space, the integral can be expanded in this way. So here, the Laurent series starts with 1 over epsilon square term, and the coefficient is area of the domain. And next comes 1 over epsilon term, and the coefficient is the length of the boundary of the domain. And we have the energy and plus higher order terms. So you have area and length. And if you consider the Steiner formula for two-dimensional domain, then again you have the area and the length, okay, as coefficients. So I hope that our Laurent series has richer information than Steiner type formula. So that's my hope. Okay. So next, I want to generalize the energy to three-dimensional domains. So suppose you have compact body omega in R3. Then you can define renormalized risk potential in the way which I have explained. And again, if a point approaches the boundary from inside the domain, then this V tends to minus infinity. But the asymptotic can be explained by this formula. So where H is the mean curvature and K is the Gauss curvature of the closest point in the boundary to point X. Okay. Then, so up to here, I think I have proof. And from here, it's ongoing. So it's not completely done. So we can define renormalized potential energy by the following. So it looks a little bit more complicated. So you can integrate V on the complement of neighborhood of the boundary, and then it explodes. So you can need a counter term to kill the explosion, and that is given by this. So you have 1 over delta square term, and the coefficient is area of the boundary, and then 1 over delta term, and the coefficient is the total mean curvature. So these two guys appear as coefficients in Steiner's formula. Okay, and in this case, you have 1 over delta term here, and unfortunately, this term is not killed in this integration. So you have log term here, unlike the case of two-dimensional domain. Okay, and the coefficient is integration of square of mean curvature and some Euler characteristic of the boundary. But here you have H in log term. So in fact, there's some ambiguity. So the factor H is put to make things scale invariant. Okay? So suppose you double the whole picture, then this term is invariant, because essentially this is dx dy over x minus y to 6th. And essentially on omega times omega. So it is 6-dimensional domain and 6 form, and you have dx dy and the distance to the 6th. So it is invariant by homotopy. And this term, so if you double the whole picture, then the area will be 4 times as big as before, but delta is also doubled. So this term is invariant. And this, the curvature will be half, and the area, the domain of integration will be 4 times. So this will be double, but this is also double, so this is invariant. But the log term has some trouble. Log of 2 delta is log delta plus log 2. So in order to kill log 2, I put log h here. But the factor h is not the unique one with this effect. For example, you can choose 2 times h, well, and so on. So there's some ambiguity in the choice of this factor to make things scale invariant. So I don't know whether this choice is the best or not. And also, I may need some additional constant term to make it invariant under Morvis transformations. So I think this definition is, in some sense, temporary. And also, I hope that this can be expanded in Laurent series with coefficients volume and area and total mean curvature and so on. And you have the energy. But I don't know for the moment the coefficients here, or I don't know whether if you have log term or not. I haven't completed the computation. Okay, so so far the preliminaries to the second part, and now I want to go to the second part. So it's a kind of generalization. Oh, no, analogy of Wiles tube formula. And from now on, I want to restrict our attention to the space of planar knots. So let's give you a planar knot. Then you consider the epsilon neighborhood of the knot. So that is a band around the knot, K. And if you take the boundary, then it's a pair of parallel curves. Okay? So you can consider the energy of this two-dimensional annulus, or otherwise Morvis energy of this link. Okay, pair of parallel curves. Then, if epsilon goes down to 0, both explode, and both can be expanded in Laurent series in this way. So the Morvis energy of this link can be expanded like this. So first, the Laurent series starts with a 1 over epsilon term, and the coefficient is the length of the original knot. And you have the energy of knot itself, and you have total curvature and higher order terms. And if you consider the energy of annulus, then again the series starts with 1 over epsilon term, and the coefficient is the length. And again you have total curvature, total squared curvature. I do not have any constant term here. And something new appears as a coefficient of epsilon square. And this can be expressed in this formula. So for the moment, I only have the formula with renormalization. So this is essentially integral of something on the product space, but remove the neighborhood of the diagonal. And the counter term is given by this. So it's 1 over epsilon cube, and you integrate something which depends on the curvature. And this function f is given as follows. So that is the last formula. And so f is the sum of two terms, one with denominator the distance to the square, and one with denominator with distance to the fourth. And the numerator is, the first one is the product of the curvatures at these 2 points times cos of angle. And the numerator can be expressed in terms of angles. So I want to explain the angle theta p and theta q. So if you have a pair of points on knots p and q, then join them by an oriented line. Then theta p and theta q are oriented angle from this oriented line to the knot. So I assume that the knot is oriented. So, this is the formula. I hope this is correct. Okay. So for the moment, I have only computed with one example. That is the simplest case. That is the round circle. So when K is a round circle, then the neighborhood is the annulus, ordinary annulus. And the energy of annulus is given by this, the annulus with 2 epsilon. So that the core has radius 1. So you don't have any constant term, but you don't have any epsilon square term. Okay. So our new functional is the coefficient of epsilon square term, and therefore it turns out that the value of our new functional at round circle vanishes. So that is, for the moment, the only example which has been computed. So I want to finish my talk with some remarks. So in this formula, you have 2 angles, theta p and theta q, and these angles appear theta q minus theta p and theta q plus theta p. And cos of the difference dp dq is the inner product of dp and dq. And this sum is equal to the conformal angle which was used in Morvis geometry. So the conformal angle is the angle between 2 circles. If you have a pair of points on knot P and Q, then you have 2 circles through P and Q. One is tangent to the knot at point P, and the other is tangent at point Q. I draw only one circle. And the conformal angle is the angle between these two circles. So I didn't draw the second circle like this, but the angle is same as the angle between this circle and the knot here. So geometrically, you can show that this angle is the sum of these two. So in this case, theta p and theta q are oriented. So theta q is positive here, but theta p is negative, and the conformal angle is negative. But anyway, so some of the terms, cos theta p and theta q, these are conformally invariant, but I don't know whether this is Morvis invariant or not. So that is not known. And also, I don't know whether this functional is essentially new or not. It might be equal to some functionals which has been known already. So that's all. Thank you.
Okay, questions for our speaker, Rob?
Jun, the going back, I don't know if you want to put on the slide, but the one with we had the log delta H. So one of the problems that Ockley and Sadoun had was they couldn't show that their version of a surface energy was bounded below, and they had the same kind of thing. We tried to actually give a kind of a geometric version that was analog to the excess length picture. There's an excess area picture where you don't compare with a plane, because always you have infinite excess area unless you're in a umbilical, but you compare with a kind of a quadratic surface near infinity. I'm wondering whether you can get bounded below for that, or whether you have maybe an excess area picture that you could use that would help you identify what additional term to include or not include. if you thought about that.
Sorry, for the moment I don't have any explanation for that.
Can you get it bounded below? Maybe it's the question. It was a comment. Here's the question: is it bound below that you can get?
So I don't know whether it is bounded below or not. Oakley and Southern defined surface energy, and in their story they had similar problem, difficulty with log term. So so this is the story of surface energy by Oakley and Southern. Again, if you have a surface in R3, you remove an epsilon neighborhood, then you have log term here. So there is some trouble with log term, and I don't know whether it's bounded below or not. And for planar domains case, for the case of planar domain, this is bounded below, and this the minimum is attained by a round disk, and that is proved. But if you want to generalize this function to, so in fact this can be expressed in the double integral of the product space of the boundary of omega. So essentially it is double integral on k times k. And that formula can be generalized to space curves, and then what you get is not bounded below. So boundedness is not an obvious problem.
In Rn, do you see any relationship between the Laurent expansion coefficients and the Minkowski functionals?
Minkowski?
Yeah, global geometric, higher order global geometric function.
I don't know. I don't know the Minkowski. Yeah, so I'm sorry.
Okay, well, let's thank our speaker again.